Okay, let's get started. So if you have a homework 4 or a quiz, what is it now, 12? Hand those in. I couldn't find your quiz 11s. I must have left them at my house, so they're not in my office, so I don't have them to give them to you. Okay. Well, you handed them in yet on Wednesday.
During lab.
Oh, during lab. Okay. Okay. I can't remember 2 days ago. We're already at that point in the semester. Okay, so are there any questions since last time? None? Okay, so what were we starting to talk about last time? PDAs, those public displays of affection, right? Yeah, obviously. So what are we really talking about? Push-down automata, yep. So we've talked about automata in several contexts now. What is the difference here between a DFA and a PDA here? So what is the fundamental difference?
This is represented as a stack. I don't know how to describe the representation of the
So, well, it's still a state machine, but what did we adorn the PDA with? What did we put onto the machine? The sixth thing.
Oh, we put a stack language.
Yeah, a stack. So we have the ability to work with a stack now. So it's essentially just an NFA plus a stack. Okay, and it actually is a non-deterministic machine. So, and that will actually become important. So it is like an NFA plus a stack. We could, if we wanted to, if there's time, at some point to talk about a deterministic version of a PDA, and that leads to interesting answers, but we're going to stick with this one for now. So what was the goal of a PDA? What did we want it to recognize? What set of languages do we want it to recognize?
Context-free.
Yeah, the context-free languages. And what currently recognizes the CFLs? So what was the thing that we introduced that does that? Yeah. Yeah, the grammars that we were talking about. So those recognize the context-free languages. And we would want a PDA to recognize the same thing. And possibly, like we did with regular languages, if there was a conversion back and forth between a grammar and a PDA, that would be handy-dandy. So what could we do about that? Well, if I want to show that these two models are equivalent, the CFG and the PDA model, what would we have to show if we want to show that they are the same? What would we have to do?
We would show in both directions that they're a subset of each other.
Yeah, so like every CFG can be converted into an equivalent PDA, and every PDA can be converted into an equivalent CFG. That's what we were doing before. We were converting a DFA into an NFA, which is pretty easy to do, and then NFA to a DFA, and that was the power set construction, for example. And we did the same thing with regexes, we did the same thing with regular grammars. So let's do the same thing here. And we're only going to tackle the easy direction today because the hard direction will take a whole class, believe it or not. So let's do the CFG to a PDA conversion. Okay, so let's see. So we're given a context-free grammar, and we want to produce an equivalent PDA for the same language. Well, that seems kind of hard to do because a context-free grammar has all these variables and rules and things, and the PDA has none of those things. It's just a state machine with a stack. So let's actually think about this for a second. And first of all, we actually should work with a PDA first. So before we actually go into the details of this, let's actually make a small PDA to recognize a simple language. So because every regular language is context-free, then if I give you a regular language, could I make a context-free grammar for it? Yeah, because every regular language is context-free. So if these models are the same, then it's not really that interesting to talk about a regular language. What is a non-regular language that is context-free? Our favorite non-regular language. 0 to the n, 1 to the n. So maybe let's try to make a PDA for 0 to the n, 1 to the n. So let's look at a PDA, PDA for 0 to the n, 1 to the n for all n at least 0. Make this a little bigger. So let's see. Well, if I just ignore the stack entirely, I don't touch the stack, well, could I ever get this language? If I just said, I don't care about that stack thing, I'm just going to stick to the states, will I ever get 0 to the n, 1 to the n? No, why not?
It's not a regular language, so.
It's not regular, and if I ignore the stack, I essentially just have an NFA on my hands, and that's not going to get us anywhere. So we have to use the stack in some way in order to get this to work. Well, let's see. Let's suppose that I have a bunch of zeros and then a bunch of ones after it, and they have the same number of them. Let's say n of them. Although the number doesn't matter, as long as it's the same, that's what matters. Well, how could I use the stack to my advantage here? Note, the stack can grow as big as you want it to be. But remember, you can only access the stuff at the top of the stack. Yeah?
Could you like stack all the zeros until you finally hit a 1 and then start popping them off every time you hit a 1 and see if you get the same?
Right, exactly. Right, so because the zeros are first and you have to match the ones to the zeros, why don't we just put all the zeros on the stack, remembering the zeros, and then once we start reading the ones, we just pop off the zeros on the stack in tandem with reading the ones. So when we read a 1, we're going to pop a 0 off the stack. Okay. Well, do we have a check for the stack is empty right now? Do we have a check for that? No, I actually said last time that we're going to address that. So one thing that you could do is, because you can put anything you want on the stack, what we can do at the start is, let's just put some special symbol at the bottom because the stack starts empty. Just put something random at the bottom. And then once we match all of the zeros and the ones, the only thing that should be left on the stack is that symbol. So, you guys like to be rich? Okay, so let's be rich. And what we're going to do is we're going to execute a transition that is going to put some special symbol on the stack, namely a $sign. Okay, so let's see. Well, if our strategy was, when we're reading a 0, we're going to put a 0 on the stack, and when we're reading a 1, we pop the 0 off the stack. If we're putting a special symbol on the stack right now, should we read anything? No. So what we're going to do is, we're not going to read anything. There's going to be more on this transition. So we're not going to read here. should we pop anything off the stack now? No, and why would that be a bad idea? There's nothing on the stack, and if you pop an empty stack, we are screwed. So we're not going to pop either. So the notation for doing that is epsilon, comma, epsilon, and I'll notate what each of these means. So the first one always means read or not. The second one after the comma means pop or not. And then now we have to say what we're going to push on the transition. So the way we're going to notate that is arrow $, or arrow whatever you're going to push. So this third one is the thing that we're going to push or not. Yeah.
Would you do this for every PDA?
You don't have to, but it actually will be vital to the CFG to PDA conversion, but it's not required at all. Yeah, you can actually just have a PDA that doesn't touch the stack at all, doesn't do push or pops, and that would just be an NFA at that point, but you can do that if you wanted to. You don't have to have this on the first transition, but it's very helpful because you know what's at the bottom now. Okay, so let's see. Well, we are going to arrive at this state over here. And so now we've notated what the bottom of the stack is. If you see a $sign on the bottom, you're at the bottom of the stack. We're never going to push another $sign on the stack. Okay, so once we do that, what was our main strategy? So, yeah.
We were going to push all the zeros into the stack.
Right, we're going to put all the zeros onto the stack in tandem with reading the zeros off of the input. Well, could there be any number of zeros on the input? Yeah, any number. So I'm going to make this a self loop. And so what are we going to read on this transition?
0.
Yeah, read a 0. Are we going to pop anything on this transition? Nope. So that's going to be epsilon. And then what are we going to push on this transition?
0.
Push a 0. Good. So that's the 0 part of the whole affair. Then now, so at some point we're going to reach 1s, hopefully. So what's going to happen is I'm going to do something here and then we can address it after. So it may seem a little weird what I'm going to do, but there's a reason for it. So I'm going to come down here and I'm going to have a transition that does nothing. It doesn't read anything. It doesn't pop anything. It doesn't push anything. Now that may seem really weird, but and we'll address why that is. But the main reason is the empty string is in this language, so I have to be able to accept the empty string. And if I say I'm going to read a 1 on this transition, then that means I have to pop a 0 in tandem with it. But that means by reading the 1, I'm not going to accept the empty string. So that's why. Okay. So then I'm going to come to this state down here, and the responsibility of this bottom state is to do the 1 part of what we're doing. So we've read all the zeros at the top. Now we got to read the 1s. So what are we going to do on the 1 transitions? So what are we going to read? 1, good. Are we going to pop anything on this transition? Yeah, namely a 0, good. And are we going to push anything? Nope, good. Because if we push anything, then we're undoing the work that we just did. So, okay. So we put all the zeros on the stack, and we match the ones with the zeros on the stack, what hopefully should remain on the bottom? The dollar sign, if everything matches up correctly. So that means that we need to go to another state where we're checking what the bottom of the stack is. So here, we're not going to read anything because the reading was responsible for pushing the zeros on and then popping the zeros off with the ones. So here, we're not going to read anything, but here we're going to pop a dollar sign because that's the only way we can check what's on the stack right now. So we can only execute this transition if the dollar sign's on the stack at the top of the stack. And because it doesn't matter how the stack actually ends, I'm just gonna not put anything on the stack, but it doesn't matter here. And at that point, if we've matched everything correctly, then we should accept at that point. Cool. And that's the PDA, yeah.
Can you explain again why we have to pop first and push in general?
Because if you are going to execute a transition where you push and pop on the same one, which could happen, then if you pushed on the stack first, the thing you want to pop is not at the top anymore. So that's why.
So like if you had more ones than zeros,
Mm-hmm. Good question.
Could you take or less? Can you just
Let's actually,
so, yeah, more ones than zeros.
yeah, let's actually go through that. So let's see what happens. So the dollar sign is going to be on the stack no matter what. Then we're going to put all the zeros on the stack, and let's say that there are more ones than zeros. Then the ones are going to match until the dollar sign's on the top, and I still have ones on the input, right?
Right.
Which means,
You didn't finish it.
but yeah, I still could take the transition to the final state. That I still can do that, but I haven't read all the input. So that's the thing that gets us. If I have more zeros than ones, then that means I'm going to put all the zeros on, match the ones, but there's going to be a zero on the top of the stack, and I have nothing left to read. So that's what's going to actually get us here. And if I have an equal number, it's pretty easy to see that we'll accept at that point. Any other questions? Yeah.
So did you say you could take the transition even if the dollar sign isn't at the top of the stack?
Right. No. So what I said was I could still take the transition. So what his example string was let's just say we have say 00111, so more ones than zeros. Well, I'm going to put 2 zeros on the stack, match 2 of them, and I still have so this is going to be red, this will be red, this will be red, this will be red, and I still have a 1 left to read. But notice the transition that goes to the final state. So the top of the stack now is the dollar sign, and the transition says we're not reading anything. So I can execute that transition. And let's just say I did. Then what happens is I go to that final state, and I still have input left to read because that last one is not read, which means I don't accept the string. You only accept the string if you've read all of it and are in the final state. Does that make sense? Okay.
Wait, so even if you have a 1 left, you will still take that transition to the final state?
I mean, the only possibility of ever accepting is going to that state in the first place. So I'm just assuming if we did take that transition because it's non-deterministic. If I did take it, then I'm stuck because I can't read that last character.
In this example, would you not be able to take the third 1 transition because there's no 0 to pop?
Right, yeah. So I can't take that 1 to 0 transition because, well, there is a 1 on the input left, but there's no 0 on the stack, so I can't take it. So both of the conditions of what you have to read and what's on the top have to be met. Yes, you got a question?
Between the pop and push, should there be a comma?
There should always be a comma.
Between
Oh, no. So this is just the notation that Sipser uses. Some other authors put commas between all three. So this is just the one that I'm used to and what Sipser does. But any other questions? Okay, so this was a relatively simple example. But let's see. So suppose that we want to actually convert any CFG into a PDA. Well, what were we doing last time? What we were doing was we were simulating the derivation on the stack. So if you remember, so I'll actually go back to it. So we had, say, this grammar right here, where we were looking at balanced parentheses, and we simulated the derivation on the stack. And what we wanted to figure out was, could we generate the string that we were interested in? And we were able to do it with these, in this derivation on the stack. So how can we do this here? Well, let's actually do an example, namely this one. So what's a grammar for 0 to the n, 1 to the n?
S to 0, S1.
Yeah, 0 s1 or, or epsilon. Okay, so relatively simple grammar. Okay, so what could we do? Well, what we were doing was we were simulating the derivation on the stack. If a variable was at the top of the stack, we applied one of the rules that it could be applied. So if s was on the top, we could either replace it with 0s1 or empty. And if a terminal was on the top of the stack, we read it off of the input at the same time that we were popping it off the stack. So if a 0 is on top of the stack and 0 is on the input, I'm going to pop them off in tandem. And at some point, well, if we've matched everything up, then there should be nothing on the stack. But do we have a check for whether the stack is empty? Do we have a pseudo check? Yeah, namely what? The dollar sign. So let's actually make a, I'm actually going to move it down here so that we have some more room. So let's make a PDA for this guy. So let's see. So we're going to have a state right here. We always need a start state. And the first order of business, of course, is to put that bottom of stack marker, the dollar sign. So let's do that in the same way. So we're not reading anything, we're not popping anything, and we're pushing a dollar sign on the stack. Good so far? Okay, cool. So let's think about what we're actually trying to do. We're trying to simulate the derivation on the stack. Well, how does every derivation start? Where does every derivation start? The start variable. So let's push on the start variable. So let's do that. And we're going to go to a state I'm going to lovingly call QLoop. And there's a reason why it's called QLoop, which we'll address in a sec. Okay. So the responsibility of QLoop is, let's figure out what's happening right now. And by that I mean, if there's a variable at the top of the stack, let's apply a rule to it. If a terminal's on top of the stack, read it off of the input and pop it off at the same time. So let's just say, for example, if zeros at the top of the stack, what should we read at the same time?
The,
What was there?
the input.
Yeah, read the input, but what are we reading off the input? If a zero's on the top of the stack, we're reading them in tandem. So if a zero's on the top of the stack, what should we read off the input?
The first zero, I guess. Or, I'm just
No,
confused here.
So we're either reading a 0 or a 1 off the input.
Right.
So if a 0's at the top of the stack, what should we read at the same time? No, you're reading the same character. So let's actually go back and think about this. So if we go back to this grammar right here, if I produce a terminal, say the left parenthesis, is it going to ever change? No, because in the derivation, you can never replace a terminal that you make. So for that reason, in the PDA, if that left parenthesis, for example, is at the top of the stack, then that means that it will never change because of how derivations work, which means that we need to read it off of the input. Remember, a PDA has an input that it needs to check whether or not it's in the language of, let's just say, balanced parentheses. So if the left parenthesis is on the top of the stack, then we need to read that same character off of the input while popping it off. The derivation is producing a string of terminals, and we're just eating up the characters that will never change along with the input. So if the entire derivation produces the string and we've read the whole input, then we have matched them up. So let's go back here. So if a 0 was produced and is at the top of the stack, what should we read off of the input? A 0. So that's what we're going to do here. So in Q loop, we're going to read a 0, going to pop a 0, and push nothing. Because the terminals don't change, we need to read off of the input in order to match what the grammar was able to produce. So the grammar is producing a string of 0s and 1s, and we're matching it up with what the grammar produced. It's either a terminal at the top or a variable at the top. If a variable's at the top, we apply a rule to it. If a terminal's at the top, then we match it up with the input. If a 1's at the top of the stack, what do we do? What do you expect?
That's it.
Yeah, it's the same thing. So if we have a 1 at the top of the stack, we're going to do very analogous things. As long as we read and pop the same character and push nothing, then we're okay. As long as they match, we're all good. Yeah.
So is the stack already like full for this one? From the start?
No. So it always starts out empty. Then we push the dollar sign on, so dollar sign's at the bottom. Then we push S on it, so S is at the top. And then we're not done with this part yet, but we're going to have rules. I mean transitions that involve popping the variable off and putting onto the stack the right-hand side. And then we'll come back to Q loop to assess what's at the top now. Other questions? Okay, so let's see. Well, how many rules do we have here in this grammar? 2 rules, okay, great. So let's do the easy one first, which is namely this one. S goes to empty. So in the derivation, that means that the variable S, if we applied this rule, goes away. So that S is going to be replaced with empty. So if S is at the top of the stack, that means we're just eliminating the S at the top of the stack and not pushing anything else. So what could we do here? Well, let's see. If we're just applying a rule, are we going to read anything off of the input? No. So I need a transition that doesn't read anything. So we're not reading anything. Let me make some room here. Then the variable s was at the top of the stack now. So that means we're going to pop it off of the stack because we want to eliminate it. We're replacing that variable with the right-hand side. So we're always going to pop the corresponding variable off first. So s is going to be popped here. If it was another variable, it would be that variable. So whatever's on the left side, because we're replacing it, we're popping it off of the stack. And because the right-hand side is epsilon, what are we going to push? Push epsilon, i.e. nothing. So that was relatively painless. Any questions about it? Oh, great, we're done. So therefore, oh, did I forget something?
The other S.
Shoot, the other rule. Okay, well, let's try to do this rule. So this one seems a little bit more complicated, right? Where we have 3 things on the right-hand side that eventually have to go on the stack in some way, right? So no matter what is the maximum number of things I could push on in one transition? Yeah, I can only push one thing on in the transition. So I'm going to need to come out of Q loop, go to some other states, and eventually come back to Q loop. So that's what we're going to do here. So let's see. So I'm going to have, and none of these are going to read for the same reason. So epsilon, we're always going to pop the left variable off, which is s in this case. But now we got to think what to push. So what should we push here? Well, let's see. Let's actually look at a derivation for now. So I'm going to move this up so that we can see what's going on. So let's say that for whatever reason, there's whatever in the stack, and let's say that s is at the top. And let's just say that we're applying the s going to 0s1 rule right here. What do I want the stack contents to be after this? So note that the s is going away and we're replacing it with the right-hand side. Yeah.
So it's going to be 0s0, or 0s.
0s1, but here's the key. Where is the 0 going to be? At the top of the stack. Okay? So 0's at the top, it gets priority, then s, then 1. Okay? Because we're reading the derivation top of the stack down because that's the place that we're accessing the character. And on the input, we're reading left to right. So we're producing the characters in the same order. So it's crucial that the 0 is at the top here. And 1 is at the bottom, quote unquote. 1's at the bottom, then s, then 0. So what does that tell us here? Which things should we push first? The 1. Okay? So when we're doing this conversion, we're always pushing the right-hand side of the rule backwards. So it's always the last character of the right side you push first because you want the left character to be at the top of the stack eventually. Does that make sense? Okay, so here, there are a number of ways you can do this and they're all equally fine. What I'm going to do is I'm going to immediately push 1 here and then go to a state. So we've popped s off, we pushed 1 on. So what is the next thing we should push according to this rule? Yeah, s. And we shouldn't pop anything here because we just pushed the 1 on. So epsilon goes to S. And then finally, what is the very last thing that we need to push in this for this particular rule? 0. Good. So then epsilon goes to 0. Sweet. So for every rule in the grammar that you have, you're going to pop the left variable and then start pushing in a sequence of transitions the right-hand side of that rule backwards. So the rightmost thing, then the next thing, then the next thing, and then the leftmost one. Well, are we done with this PDA? How can you tell? Yeah, there's no final state. So this PDA accepts nothing. So what should we do? Well, let's think about it. If everything matches up, so we made the derivation on the stack, and we're matching things up on the input, and everything completely matches up, what should be at the bottom of the stack? The dollar symbol. Yep. So that means because they matched up, what should I do? Pop the dollar sign. That's how I check that it's there. But what should I do? What should the machine do? It's a 6-letter word. Accept. Yeah. Because if everything matches up, that means the input that we read was able to be produced by the grammar, quote unquote, because we just embedded the grammar into the PDA like this. So here, we're going to go to a 4th state, or I guess a 6th state. Epsilon dollar sign goes to, let's just say epsilon, I want to make the stack clean, and then go to a final state. Okay. Yeah.
For the last rule, why don't we read an epsilon? I mean, sorry, why don't we read a dollar sign?
So note that the input of the grammar is 0s and 1s. So the input alphabet here is only 0s and 1s. Whereas the stack alphabet can have anything that it wants. So we're never going to read a dollar sign, but we can put one on the stack. So it's not tied to the input alphabet necessarily. Any questions about that? Yeah.
So this is showing it like a specific conversion,
Right.
It
Yeah, go ahead.
doesn't like generally apply. I mean, that's every CFG.
So let's actually think about that. That's absolutely what you all should be asking whenever you see a specific example, whether this actually works in general. So let's think about it. Look at these 4 states right here. So these middle 4 states. If I have any grammar, can I make those 4 states? Like the transitions between them too? Yeah, because the dollar sign is not tied to any grammar, and I just push whatever the start variable is of the grammar. So that's fine. What about these, not those, what about these 2 transitions right here? Could this generalize to any grammar? Yeah, you make one of those for each terminal of the grammar. So if I have terminals A, B, C, then I'm going to make 3 of those transitions. AA goes to epsilon, BB goes to epsilon, CC goes to epsilon. So that's generalizable to any grammar. What about these transitions in purple? Or I guess set of transitions. So what do those represent? Yeah.
It's like a connected string of terminals and variables.
Well, yeah, but like, what does each one of them represent in the original grammar? A rule, exactly. So for each rule in the grammar, what do? You have a set of transitions that goes out from the loop state and eventually comes back, where each one of them doesn't read. The first one pops the left variable because you're going to replace it, and then you push the right-hand side of the rule backwards. So this is generalizable to any grammar. Yep. To any grammar. So that tells us here that any, so this is a theorem, any CFG can be converted into an equivalent PDA. Yeah.
Just so that it's, I have in my notes, could you label each of those blocks again, just so that?
Yeah, sure. I don't know what you mean by a relabel, though.
Yeah, because like you had mentioned, like the bottom one branching off of Q loop would be like the rule.
Yeah.
For each rule application. So like, what is the red box?
So those are what this is just my term. I call these the base states. So these four are in there regardless of the grammar at all. The blue ones, so each of those are for each terminal, if I can spell terminal, of the CFG. And the purple ones are for each rule of the CFG. If I can spell of the CFG. It's Friday. I can't spell of. Yeah, so the four base states, those will always be there regardless of the grammar. The blue ones are for each of the terminals in the grammar, and the purple ones are for each rule in the grammar. Yeah, so this works for any grammar because there was nothing specific about this grammar that we had to think about, like whether or not this was possible. We just applied, looked at the structure of the grammar and just said one of those for each of the terminals, one of those for each of the rules, and that was it. For the epsilon s to epsilon 1 at the top, that was actually just a shorthand. You could have a transition that goes out and then comes back, where, like the one at the bottom, it doesn't really matter. But if there are multiple things on the right-hand side, then you're going to have to come out with multiple transitions like this. But, yeah. Any questions about this? Okay, cool. So that tells us that every every PDA can recognize a context-free language, because if you have a context-free language in mind, there's a grammar for it, and this tells us how to make the PDA for it. Now the question is, well, could a PDA recognize a language that's not context-free, which we don't know exists yet, but it might be possible. So what we're going to eventually show and not get to all of today is that any PDA can be converted into an equivalent CFG. So this one, I'm just going to let you know right now, is significantly harder. Or at least more involved. The idea is relatively simple, but it has a lot of details to go with it. So you could say, well, every PDA has this form, so just basically undo or do this construction in reverse. Is that true? Does every PDA look like this? No. In fact, look at the PDA we made before. It has the
Base.
the base parts, right. So it has some of the base parts, but it has these self loops at multiple locations. So it doesn't necessarily have the right form. I mean, it's close, but it's not quite the right form. So we can't say that this works for any CFG just by reversing the logic that we did before. So we're going to have to, if this is true, we're going to have to think a little bit harder about this. So let's see. Well, let's see. So what can we do about this? So here's my first claim to help us along with this. So for any PDA, there is a PDA with the same language with exactly one final state and can, and I'm going to underline can there, can empty its stack in that final state. I know it's a mouthful, but each one of those words is important. So what am I saying? I'm saying here that not only can we get a PDA with exactly one final state, but we can also get a PDA with a one final state that allows itself to empty the stack if it wants to. It doesn't have to, but it can if it wants to. So that's what I'm saying here. So I claim that this is true. So let's ignore the empty stacking part. Let's just focus on the one final state. So can I, from any PDA, convert it into a PDA with one final state? Yeah, so how do we do that?
I guess the same way we do it for every example. We read nothing, push nothing. And,
Okay, so let's just say that we have a PDA right here.
from every final state.
Okay, so let's just say we have 3 of them. What do? We
We make a transition to another final state.
Let's make a new final state. Okay, going from 3 to 4, that's going further from 1. So what do we do? And what do we do? You got the right idea.
From each original final state, we make a transition to the new final state that reads nothing, pushes nothing, and pops nothing.
Okay, so we just have a bunch of do nothing transitions. Okay, so epsilon goes to epsilon for all 3 of these. Okay, cool. So does this work? Does it matter what the stack contents are when I accept a string? No, so I can have anything on the stack that I want to. So if I landed in one of those 3 final states before, I can just zoom over to that one final state. So it's just like the NFA idea that we had before. Now let's tackle the empty the stack contents if it wants to part. So could it be that the stack was empty in the original final states? Could that be possible? Yeah. So in those situations, in this new final state, we end with an empty stack too, because we don't change anything along the way there. But could it be that I had stuff on the stack and now I end up with things on the stack? Yeah. So what we're going to do here is have a bunch of self loops, which are epsilon have it backwards, comma, A goes to epsilon for each A in the stack alphabet. So for each possible thing on the stack, I'm going to have a transition that you don't read anything on it, so therefore you don't have to take it. But if you do, you can pop the things off the stack if you wanted to. So this allows us to actually empty the stack. And this will actually be very important, which we'll address on Monday. So I'll see you then.